So a very good evening everyone. Just quickly confirm audio video is clear. Everything is good. Just kindly quickly confirm audio video is clear. Just quickly confirm me once whether audio video is clear, everything is going good. And then we will start this energetic section of structural analysis. I hope all of you have seen the previous sessions of environmental engineering and strength of material. In that we have discussed very important question from GATE point of view. And today we will going to discuss about structural analysis. But first, kindly confirm audio video is clear, everything is going good. Just quickly confirm me once. Good evening. Good evening, Mathan. Audio video is clear? Audio video is fine? Just quickly confirm me once. Yes, sir. Okay. So today's session is about the structural analysis, one of the most scoring area for civil engineering students in upcoming GATE 25 examination. My dear, I have told you this several times that in GATE examination, especially from this structural analysis, you will see very easy questions. So if any question comes from this subject, make sure that you don't commit any silly mistake and you score 100% at least in this subject in upcoming GATE examination. Okay. Before starting the session, I would just like to make few announcements. First is regarding our Test Series Plus program, and this program is offered to you at a discounted price of 20%, where we are providing you with India's largest test series along with the GATE question bank of maths and aptitude. We are also providing you with the doubt solving portal, online revision and score booster sessions, post-GATE guidance and PSU and MS mock interviews if required when you get a good GATE score. We at IMS GATE Academy, my dear, we conduct 800 hours of live teaching in 4 different types of program that we offered. It's starting from live online program, hybrid program, offline program and the self-learning program where we provide you with the theory and exercise book. Especially in our exercise book, there are more than 4,000 practice questions, well versed in level 1, level 2 and level 3. Along with that, we are providing you with the GATE question bank of last 33 to 34 years. In which we provide you with the detailed solution, alternate solution, key points and chapter overview. We provide you with the 12 personalized one-to-one mentoring session, the flagship program conducted at IMS GATE Academy, along with the India's largest test series containing 130 plus tests, is starting from the chapter test, subject test, multiple subject test, advanced subject test and the full-length mock test. If you want to know more about our program or the courses that we offer, you can book a free online session for which the link is provided to you in the description box. Even if you want to register for our Test Series Plus course, you can again find a Google form link which is there in the description box. By these words, I would just like to start my energetic section of structural analysis. Today, I just want the free, full support of yours. Whenever we will going to discuss any question, I want answers and solutions from your end. This is the total course flow of structural analysis, starting from degree of static indeterminacy, truss analysis, force method of analysis, displacement method of analysis, influence line diagram, arches and cables and the matrix method. In these topics, the very easy scoring area is degree of static and kinematic indeterminacy. Then you have one common topic of truss analysis, which is common with engineering mechanics as well. Then you find the force method and the displacement method of analysis, in which in force method you are getting more frequent and easy questions. Very 4 simple methods are there in force method and we will going to see all the questions today itself. Then you have the influence line diagram, again one of the major area from where you can get a good quality question in the GATE examination. Okay, chalo, let's start with this. First of all, my dear students, if we talk about the subject of structural analysis, structural analysis means determining the unknown forces and the unknown deformations. Now, in order to find out how many unknown forces are present in the structure, you need to calculate the degree of static indeterminacy. Unknown forces includes unknown support reaction and unknown member forces. So the number of unknown support reactions are determined using degree of external indeterminacy and the number of unknown member forces are determined using degree of internal indeterminacy. And when you just add these two things, you will find out the degree of total or degree of static indeterminacy of the structure. So basically we have four different types of structure. Majorly they are pin jointed and the rigid jointed structure. In pin jointed structure, we have pin jointed plane frame, that is a 2D truss, or pin jointed space frame, that is a 3D truss. Okay, then we have rigid jointed structure. Again we have rigid jointed plane frame and rigid jointed space frame. Talking about pin jointed plane frame, first of all it's a coplanar non-concurrent force system. For a coplanar non-concurrent force system, you have three equations of static equilibrium. That is why the degree of static indeterminacy is the sum of external plus internal indeterminacy, where external indeterminacy is number of unknown support reactions minus the number of equilibrium equation, that is R minus 3. And the degree of internal indeterminacy for a pin jointed space frame is equal to m minus 2j plus 3, where m is the number of members, j is the number of joints, and using this you can calculate the degree of internal indeterminacy. And if you take the sum of external and internal indeterminacy, you will get the degree of static indeterminacy, that is m minus 2j plus r. Okay, let's see this question. Here one truss is given to you. You need to find out the degree of static indeterminacy for this truss. I am just giving you 1 minute of time because we have to solve a lot of questions today. Keep answering your answers in the chat box. You have just 1 minute of time, go for it. 1 minute of time for you, just go for it. It's a pin jointed plane frame. You need to find out the degree of static indeterminacy for this pin jointed plane frame. Please go for it. Go for it, go for it. You can always write your answers in short, or in, if you want anything to be discussed precisely, that also can be written in the chat box. Please go for it. Okay, so let me solve this in a very basic way, right? First of all, how many number of unknown support reactions here? So you can see this is a hinge joint, hinge support, sorry. So you have 1 and 2 unknown support reactions here and 1 and 2 unknown support reactions here. So total number of unknown support reactions is equal to 4. So degree of external indeterminacy is equal to R minus 3, that is 4 minus 3, which is equal to 1. So degree of external indeterminacy for this truss is equal to 1. Now coming to the internal indeterminacy, you need to count the number of members. So check this out. This is 1 member, 2 member, then this is 3, 4, 5, then this is 6, 7, 8, 9, then this is 10, 11, 12, 13, 14, 15, 16, 17, and in total of 18 members. In total of 18 members. So M is equals to 18. Now how many joints you have? Just count the number of joints. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 joints. In total you have 11 joints. So degree of internal indeterminacy DSI is equal to m minus 2j plus 3. M minus 2j plus 3, right? Substitute the values. So m is equals to 18, 18 minus 2 into 11 plus 3. Please find out this value. Please calculate this value. Please calculate this value. This is 18 plus 3. 18 plus 3 is 21 and this is 22. So this will be minus 1. Just calculate this. Is it minus 1? Is this coming out as minus 1? Please tell me the answer. Is it coming out as minus 1? So DSI is coming out as minus 1. DSE is coming out as 1. So degree of static indeterminacy DS is the sum of DSE plus DSI. So DS is equals to DSE plus DSI. So this is equal to 1 minus 1. So ds of this truss is coming out as 0. So degree of static indeterminacy for the truss is coming out as 0. Just quickly reply everyone, are you getting the same answer or some other answers you are getting? Just everyone quickly reply in the chat box, please. Are you getting the same answer or you are getting some different answers? Please quickly reply in the chat box. Same answers, everyone? Please reply quickly. We have to see a lot of questions today. I want so much of energy from you now. You just keep commenting your answers, right? Don't be in a hurry to write the question. Anyways, PDF will be provided to you in the Telegram group. So all the enrolled students and the non-enrolled students, you can join a Telegram group for this lecture PDF. It will be provided to you. Just quickly confirm whether you are getting this answer or you are getting something else. Quickly reply on this. Are you getting the same answer or you are getting something else? Please reply on this. Same answers? Please reply. Kindly quickly confirm this. Are you getting the same answer or you are getting something else? Chalo, I hope you are getting the same answer. Moving ahead with the next question. This is the next question in which you need to find out the degree of static indeterminacy for a pin jointed plane frame. Again, 1 minute of time for you. Just go for it. Please go for it. Okay, let's check this out. The question says that the degree of static indeterminacy for the pin jointed plane frame is. First of all, you need to find out the degree of external indeterminacy. So ds is equals to dse is equals to r minus 3. How many support reactions? You have 2 support reactions here and 2 support reactions here. In total, 4 support reactions. So this is equal to 4 minus 3 and 4 minus 3 is equals to 1. Okay. Now calculate the degree of internal indeterminacy, that is equal to m minus 2j plus 3. So number of members are, you have 1, 2, then you have 3, 4 members, then this is 5, then this one is 6, this is 7, then this is 8. Okay, sir. So 1, 2, 3, 4, 5, 6, 7, 8, and this one is 9 and this one is 10. So in total you have 10 members here. So m is equals to 10. Just count the number of joints. So you have 1, 2, 3, 4, 5 joints here. So number of joints is 5. So dsi is equals to m minus 2j plus 3. So this will be 10 minus 2 into 5 plus 3. So this will be how much? So this is 10 plus 3, 13. 13 minus 8 will be 5. So dsi is coming out as 5. Okay. Just write down the degree of static indeterminacy. ds is equals to dse plus dsi. You can also use the direct formula, but intentionally I am doing it like this. You can use the direct formula that ds is equals to m minus 2j plus r, but intentionally I am calculating degree of external and internal indeterminacy, because in some of the years we have seen, not in GATE examination but for other examinations, we have seen that they also, in sometimes they ask you the difference between is internal and external indeterminacy. So like this you can solve. So ds is equal to external is how much? External is 1 and internal indeterminacy is 5. So degree of static indeterminacy for this structure is equal to 6. Okay. So this 6 is my correct answer for this structure. So for a pin jointed plane frame, the degree of static indeterminacy can be calculated like this. Let's move ahead with the next thing. Now for pin jointed space frame, that is we are talking about a 3D truss. For a 3D truss, the number of equilibrium equations available are 6. Okay. Therefore, the degree of external indeterminacy is equal to total number of unknown support reactions minus equilibrium equation. That is why it comes out as R minus 6. And degree of internal indeterminacy is M minus 3J plus 6. When you add both of them, you will get the degree of static indeterminacy, which is M minus 3J plus R. Let's quickly see one question here. Let me draw one 3D truss like this. Say this is a 3D truss. This is a 3D truss. Calculate the degree of static indeterminacy for this 3D truss. Calculate the degree of static indeterminacy for this 3D truss. Can you tell me how many support reactions are present here? Can anybody quickly answer this? How many support reactions are present for this 3D truss? How many support reactions are present? So if you have to count the number of support reaction, you can see for every hinge support, you have 3 support reactions, 1, 2 and 3. For a roller support, there is only 1 support reaction. And again for a hinge support, you have 3 support reactions like this. So in total, you have 7 support reactions here. Count the number of members. So you have 1, 2, 3, 4, 5, 6 members. Number of members are 6. Then number of joints. How many joints you can see here? 1, 2, 3 and 4 joints in total. So number of joints are 4. So degree of static indeterminacy is equals to degree of external plus degree of internal indeterminacy. So when you take this sum, this will be M minus 3J plus R. You can also calculate separately. We have already done it for the previous 2 questions. For this question, I am doing it directly. So ds is equals to M is 6 minus 3 into number of joints. Number of joints are 4 and number of support reactions are 7. Please calculate this. So this will be 13 minus 12. So degree of static indeterminacy for this space frame is equal to 1. So this is how you can deal with a pin jointed plane frame and a pin jointed space frame. Let's move ahead with this. Now next is the degree of static indeterminacy for the rigid frames. Rigid jointed frames are 2 types. First one is the beams and second one is the portal frame. I would like to tell you one simple thing. Whenever we talk about beams, so rigid jointed frames are of 2 types. Rigid jointed frames are of 2 types. First one is the beams. And if I talk about beam, in beams there are 2 types of unknown forces. In beams there are 2 types of unknown forces. There are 2 types of unknown forces. That is, first one is the support reactions. And second one is the internal member forces. Second one is internal member forces. Now sir, what are internal member forces in a beam? Internal member forces in a beam includes axial force, then it includes shear force, and then it includes bending moment. What is the important point here? For a beam, if you know the value of support reactions, you can find out these axial forces at any section. That is why we say that beams are always internally determinate. Degree of internal indeterminacy of beam is always equal to 0. So if we write down the degree of static indeterminacy for the beam, degree of static indeterminacy for the beam is equals to degree of external indeterminacy plus degree of internal indeterminacy. Since all these member forces can be calculated if you know the value of the support reaction. Therefore, we say that for beams, degree of internal indeterminacy is equal to 0. A very, very important result that you should remember every time when you are dealing with the beam. Okay, sir. Now, if hybrid joints are present, then the degree of static indeterminacy for the beam can be written like this. So, degree of static indeterminacy for the beam is only due to the external indeterminacy, and this is equal to R minus 3 minus extra equilibrium equations, minus extra equilibrium equations, minus extra equilibrium equations, minus extra equilibrium equations, minus extra equilibrium equations due to hybrid joints, minus extra equilibrium equations due to hybrid joints, due to hybrid joints. Now, in some of the question, if they say that the members are axially rigid, then you have to also subtract the number of axially rigid members to find out the degree of static indeterminacy. Okay, let's see some questions from here. So, this is for a rigid jointed plane frame. First one is the beam. Degree of static indeterminacy for the beam is degree of external plus internal minus force releases. So, force releases are the extra equilibrium equations that you get. Good evening, Richa. Good evening. Then you can see that for vertical loading, number of equilibrium equations taken will be 2. For general loading, the number of equilibrium equations taken will be 3. In vertical loading, we don't consider the horizontal support reaction and we don't consider the horizontal equilibrium equation. In general loading, we consider all the support reactions and all the equilibrium equations. Okay, sir. Then for force releases, if you have an internal hinge and using the internal hinge, the number of members connected is M dash, then the total number of extra equilibrium equations that you will get will be M dash minus 1. Then the second hybrid joint is the shear hinge, and if shear hinge is present, you will get 1 extra equilibrium equation. For internal link, you will get 2 extra equilibrium equation. Second, similarly for internal roller support, again you will get 1 extra equilibrium equation. I think for this internal roller support, again you will get 2 extra equilibrium equations. 2 extra equilibrium equations for internal roller support. Let's move ahead with this. A beam is given to you. You need to find out the degree of static indeterminacy for the beam. Please calculate this. So, you have a beam like this in which an internal hinge is present here. So, let me name this beam. This is a fixed support here and an internal hinge is present at B. An internal hinge is present at B. Calculate the answer and tell me. An internal hinge is present at B. Then this is point C with a roller support and D with a hinge support. Please calculate this. It's very easy. Whenever degree of static indeterminacy comes for a beam, it is really very easy to find out. You have to just count the number of support reactions. So, you can see here you have 3 support reactions, here you have 1 support reaction and here you have 2 support reactions. So, in total 3 plus 1 4 and 4 plus 2 6. So, the number of support reactions is equal to 6. Number of equilibrium equations. So, number of equilibrium equation is 3 are the conventional equilibrium equation plus 1 extra you will have due to this internal hinge. So, I will write down degree of static indeterminacy for the beam is equal to R minus S, that is equal to 6 minus 3 minus 1. So, you can easily find out the value of ds. ds will come out as 6 minus 4, that is equal to 2. Degree of static indeterminacy for the beam is coming out as 2. Okay. So, let's see the next question. Another beam is given to you with an internal link here. You need to find out the degree of static indeterminacy for the beam. The manner in which I am showing you the solution, you kindly follow the same way. Okay. So, you can see here, this is your support A. It is a fixed support. Then you have a roller support at B. Then you have internal link at CD. And then again you have a hinge support at E. So, this is your internal link. This is your internal link. This is internal link, right? Now, first of all, how many support reactions do you see over the beam? So, the number of support reactions here are 3 support reactions here, 1 support reaction here and 2 support reaction here. So, this is 3 plus 3, 6. number of equilibrium equations. So S is equals to, you have 3 conventional equilibrium equation, and apart from that, due to this internal link, there will be 2 additional equilibrium equations. So I will write down 3 plus 2 here. So total number of equilibrium equations available is 5. So degree of static indeterminacy is equal to R minus S, that is equal to 6 minus 3 minus 2. So degree of static indeterminacy for the beam will come out as 1. So like this, you need to deal with the questions in which a beam is containing the hybrid joints. Okay, sir. Let's move ahead with the next question. Next is about the rigid jointed plane frames. For rigid jointed plane frames, there are basically 3 methods to find out the degree of static indeterminacy. As per the first method, where you need to count the number of members, number of joints and number of support reactions, the formula will come out at ds is equals to 3m plus r minus 3j. And if any hybrid joints are present, then you have to subtract the number of force releases. Okay. So this is as per the first method. As per first method, the degree of external indeterminacy is r minus 3 and degree of internal indeterminacy will be 3m minus 3j plus 3. All the formulas you should remember, because you never know which method will be easy in the examination. So you should remember all these methods, all these formulas to calculate degree of static indeterminacy for a rigid jointed plane frame. Let's move ahead with this. This is the method number 1. As per method number 2, you have to count the number of closed loops. You have to count the number of closed loops. As per method number 2, degree of static indeterminacy is equals to r minus 3 plus 3c, and c is the number of closed loops. Again in this method, if hybrid joints are present, you have to subtract the number of extra equilibrium equations which are termed as force releases. You have to subtract here force releases. But my favorite method is the third method, in which you have to cut the frame in order to get independent cantilever components. Then you have to restrain all the unstable members and joints, and that is how you can find out the degree of static indeterminacy. As per method number 3, degree of static indeterminacy is equals to 3c dash minus n. It is equal to 3c dash minus n. Then there will be no force releases here. Intentionally I have written this to cut and tell you that there will be no force releases here. All the force releases will be counted in this number of restraints that you provide. Okay. So as per method number 3, degree of static indeterminacy is equals to 3c dash minus n. Okay, sir. Let's see some questions regarding this. This is a GATE 2019 question, and in which you need to find out the degree of static indeterminacy. Have 1 minute of time and tell me the answer here quickly. Keep commenting your answers in the chat box, right? I'm telling you, just stay with me for 3 hours and I'll make sure that you revise complete structural analysis. Please do this question and tell me the answer in the chat box. Keep commenting your answers. Keep commenting your answers. Keep commenting your answers. Keep commenting your answers. So if you apply method number 1 and method number 2, it will become very clumsy, like it will become very bulky for you. That is why my favorite method is method number 3. So you can see here, there are basically 3 supports. So for this entire portal frame, you need to cut it in such a way that you will get 3 cantilever components. So sir, how many cuts are required? So one cut I will apply here, another cut I'll apply here, and another cut I'll apply here. Then one cut here, one cut here, and one cut here. How many number of cuts required? So number of cuts C dash required is 6. Okay, sir. So you have 3 independent cantilever components. Now you have to check the stability of these independent cantilever components. When you see this first cantilever component, everything is stable up to this hinge. But when you observe this portion of the hinge, this part of the member which is on the right side of hinge, you require one moment restraint in order to stabilize this. You require one moment restraint here in order to stabilize this part of the member. Okay, sir. So if you apply one moment restraint here, then this first cantilever component will become stable. Now come to the middle cantilever component. In this middle cantilever component, you require one moment restraint here in order to stabilize this middle cantilever component. You require one moment restraint at this hinge support in order to stabilize this middle cantilever component. Now coming to this third cantilever component, again here you require one moment restraint in order to stabilize this third cantilever component. So how many restraints are required? 1, 2 and 3. In total, 3 restraints are required. So the value of n is equal to 3. So directly you can write down degree of static indeterminacy is equal to 3c dash minus n without any confusion. If you apply the second method where you count the number of closed loops, so what we have observed is whenever you have these free ends, please don't apply method number 2. And in fact, method number 1 will be more bulky. So why to go for it? Just apply this, an easy method. So ds is equals to 3 into 6 minus 3. So this is 18 minus 3. So degree of static indeterminacy here will come out as 15. Just quickly say yes or no if you are getting the same answer. Kindly quickly confirm yes or no if you are getting the same answer or if you are getting some other answer. Kindly just confirm me once. My dear, please start, like, whatever answers you are getting, kindly please comment so that I can have the idea if you are solving it properly or not. So degree of static indeterminacy for this portal frame is equal to 15. Okay, sir. Let's move to the next question. Next question is saying that the degree of static indeterminacy for the rigid frame having 2 internal hinges as shown in the figure. Yes, sir, easy thing. Method number 3. How many supports? You have 3 supports. For 3 supports, how many cantilever components are required? 3 cantilever components. Do it. I am just giving you 1 minute of time. Go for it and solve this. Go for it and solve this portal frame and calculate degree of static indeterminacy for this portal frame. Please go for it. Go for it. Go for it. Please go for it. Go for it and keep commenting your answers, everyone, please. We will going to revise complete structural analysis, but do this quickly. Get me the value of degree of static indeterminacy for this portal frame. Everyone keep replying everyone, whatever answers you are getting. Chalo, let's see this. You have 3 supports here. So how many cantilever components you want? 3 cantilever components. For 3 cantilever components, how many cuts are required? I'll do 1 cut here, another cut here. Then I'll do 1 cut here and another cut here. Okay. So like that, number of cuts required to have 3 independent cantilever components are 4. So number of cuts required is 4. C dash is equal to 4. Now let's stabilize all the cantilever components. So this first cantilever component is not stable. It will going to fall because of this hinge. So what we will do is one moment restraint is required here. So one moment restraint we will going to provide over this hinge support. Now coming to this middle cantilever component, since it's a roller support, it can move freely in the over the surface and it can also turn about this point, means it can also rotate, right? So in order to stabilize this roller support, you require one horizontal reaction restraint, and you will require one moment restraint here. So number of restraint required are 2 over this roller support in order to stabilize it. Now let's move ahead. So we have stabilized this roller support. On moving ahead, we coming to this internal hinge. So till this internal hinge, everything is stable. but this portion which is connected with the internal hinge requires one moment restraint in order to have stability. Similarly, coming over to this internal hinge, everything is stable, but in order to stabilize this portion of the member, you require one moment restraint here. So the total number of restraint required here is 1 and here is also 1. Now coming to the third cantilever component, since it's a roller support, in order to stabilize this roller support, you require one horizontal reaction restraint and you require one moment restraint here. So N is equals to 2 here. So just count the number of restraints. So this is 2. 2 plus 2 is 4. 4 plus 1 is 5. 6 and 7. Total number of 7 restraints are required. So N is equals to 7. Calculate degree of static indeterminacy. This is equals to 3C dash minus N. So this is equals to 3 into 4 minus 7. So 12 minus 7 will be how much? 12 minus 7 will be equal to 5. So degree of static indeterminacy for this rigid jointed plane frame is equal to 5. Okay, sir. So this is how you can solve. This is a GATE 2008 question asked for 2 marks. Just see, we have taken the 2 marks in no time. Let's move ahead to the next question. This is a 1987 question, very old. Still, it's one of the fantastic question that is placed in the degree of static indeterminacy. You need to find out the degree of static indeterminacy for the structure shown below. Please do it. Again, just 1 minute of time for you. Go for it and tell me what is the answer for this question. Just 1 minute of time for you. Go for it and tell me what is the answer for this question. Everyone keep replying. Keep replying, everyone. Whatever answer you are getting, please keep on replying in the chat box. Keep replying, keep replying. Quickly reply. Keep replying your answers. Okay. So for this, how many supports are present? So you have 3 supports. So how many independent cantilever components are required? 3 independent cantilever components are required. So for this first support, you will apply one cut like this, another cut like this. Then you will apply one cut here and another cut here, right? So in total 4 cuts are required to get 3 independent cantilever components. So C dash is equals to 4, okay? Now just count the number of restraints. So when you observe this first cantilever component, it is stable throughout. This middle cantilever component will require one moment restraint over this hinge support. So N is equals to 1 here. Then when you observe this third cantilever component, will require one moment restraint and one horizontal reaction restraint here. So N is equals to 2. So in total, how many restraints are required? 3. In total, you have 3 restraints. N is equals to 3. So ds is equals to 3c dash minus n. This is equals to 3c dash minus n, which is equals to 3 into 4 minus 3. So ds will be how much? ds will be equal to 12 minus 3 will be 9. Degree of static indeterminacy for this portal frame is equal to 9, right? Yeah. You can check your answers, Prajat, right? Degree of static indeterminacy for this portal frame is equal to 9, 3c dash minus n. Okay, sir. Let's move ahead with the next thing. This is one structure given to you, and this structure intentionally I have kept because axial shear hinge, vertical shear hinge, both are present, and for this portal frame, you need to find out the degree of static indeterminacy. Have 1 minute of time and calculate the degree of static indeterminacy for this portal frame. Go for it. Please go for it. Keep commenting your answers. What is the degree of static indeterminacy for this portal frame? So see this, you have one fixed support here, roller support here and another fixed support here. So how many cantilever components are required? 3 cantilever components. So you will do one cut here, another cut here, and then you will do one cut here and another cut here. Okay, sir. So number of cuts required are 4. C dash is equal to 4. Now check into the number of restraints. So this first cantilever component is totally stable. So no restraints are required. Coming to this cantilever component, starting from the roller support, you require 2 restraints. One horizontal reaction restraint and one moment restraint is required. So number of restraint required at roller support is 2. Let's move ahead and come to this vertical shear hinge. So till this point, everything is stable. But when you observe this portion of the member, this requires one vertical reaction restraint. So one vertical reaction restraint is required to stabilize this portion of the member. Similarly, when you come to this vertical shear hinge, this portion of the member needs to be stabilized by providing one vertical reaction restraint. So one restraint is required here. Now let's move ahead and come to this axial shear hinge. So now everything is stable till this situation, and when you come here and come to this axial shear hinge, this member will require one horizontal reaction restraint. This member will require one horizontal reaction restraint. Similarly, this member will also require one horizontal reaction restraint, right? So after applying all these restraints, now this middle cantilever component is also stable. Now coming to this last cantilever component, it is already stable because this is a fixed support. Just count the number of restraints: 1, 2, 3, 4, 5 and 6. So n is equals to 6. So ds is equals to 3c dash minus n, 3c dash minus n. So this is equals to 3 into 4 minus 6. So this is 12 minus 6. So degree of static indeterminacy is equals to 6. Very good answer, Prajat. Absolutely correct answer. Degree of static indeterminacy for this portal frame is 6. Absolutely correct answer. Let's move ahead with the next thing. The last portion is, although we haven't seen any question till date, but in case if any 3D rigid frame is given to you, for a 3D rigid frame, the degree of static indeterminacy is equals to 6m plus r minus 6j. This is as per method number 1. As per method number 2, the degree of static indeterminacy is equal to r minus 6 plus c, and if hybrid joints are present, you need to subtract the number of force releases, that is extra equilibrium equation. So I will write down r minus 6 plus c minus force releases, Okay, this is as per method number 2. As per method number 3, it is simply equal to 6c dash minus n, where again c dash is the number of cuts required to have independent cantilever components. So you can have this formula directly. Okay, in fact, I should do anything here. This is the formula, 6c dash minus n. So this is for a rigid jointed space frame. Till date, we haven't seen any question. Now coming to the degree of kinematic indeterminacy. So I told you that the degree of static indeterminacy gives you the detail about the number of unknown forces. Similarly, the degree of kinematic indeterminacy will tell us about the unknown deformations. How many unknown deformations we need to find out in a structure. That is calculated using degree of kinematic indeterminacy, which is also called as degree of freedom. Now sir, few things you need to remember that is to be remembered, because that is how we will going to calculate. First of all, degree of kinematic indeterminacy is analyzed as per the joints. Okay. So first of all, if you have a hinge support, the degree of freedom is 1. For roller support, degree of freedom is 2. For guided roller support, degree of freedom is 1. And for fixed support, the degree of freedom is 0. Everything we have seen in the class. Then for the types of support and the degree of kinematic indeterminacy, for example, not types of support, for joints. For pin jointed plane frame, every joint has 2 degrees of freedom, that is delta x and delta y. For pin jointed space frame, the degree of freedom is 3 for every joint, delta x, delta y and delta z. For rigid jointed plane frame, the degree of freedom is 3 for every joint, that is delta x, delta y and theta z. Similarly, for rigid jointed space frame, the degree of freedom is 6, delta x, delta y, delta z, theta x, theta y and theta z. This is for every joint, for rigid joint in space frame. Next is, if you have the hybrid joints, why I have written this everywhere? This is for hybrid joints. This is for hybrid joints. The degree of freedom for hybrid joint is, if you have the axial shear hinge and two members are connected using axial shear hinge, then the degree of freedom of that axial shear hinge will be 4. For vertical shear hinge, the degree of freedom is again 4. For internal hinge, now it depends on the number of members. If two members are connected, then the degree of freedom will be 4. But if n number of members are connected, then the degree of freedom for internal hinge will be equal to n plus 2. When it is n plus 2, when there are n number of members connected using the internal hinge. Chalo, let's see this. So this is about pin jointed plane frame. I have given you the complete summary, right? So for extensible members, this is for rigid jointed plane frame. For extensible members, degree of freedom is 3j minus r plus extra degree of freedom due to hybrid joints. For inextensible members, degree of freedom is equals to 3j minus r minus m plus extra degree of freedom due to hybrid joints. Next, for pin jointed plane frame, degree of freedom is equals to 2j minus r. For every joint, degree of freedom is 2. And for pin jointed space frame, degree of freedom is 3j minus r. Then you have for frames, for inextensible member, the degree of freedom will be 3j minus r plus extra degree of freedom due to hybrid joints. And for inextensible member, this is the formula. I think this is for beams and this is for frames. Similar values. Check this out. A beam is given to you and you need to find out the degree of kinematic indeterminacy for this beam. Please do it. You have to move joint by joint, and whenever you calculate the degree of kinematic indeterminacy, I don't want you to use the formula, use the trick that I have showed you in the class. Okay. So this is your fixed support, this is your roller support, and this one is your again a roller support. Okay. So for a beam, all these joints are which type of joints? Rigid joint. Now please calculate degree of kinematic indeterminacy. Calculate the degree of kinematic indeterminacy. Okay, check this out. This is one rigid joint, right? For a rigid joint, how many degree of freedom? You have delta x, delta y and theta z. The 3 degree of freedom are there. But due to this vertical reaction, there will be no delta y. Due to this horizontal reaction, there will be no delta x. So only 1 degree of freedom is associated with this joint. Now come to this joint. Again, this joint has 1, 2 and 3 degree of freedom. Okay, 1 second. It's a roller support. So there will be no horizontal reaction here. Sorry. So for this hybrid joint, you have delta x, delta y and theta z. So for this roller support, there will be only 1 support reaction. And due to this support reaction, there will be no delta y. But you will going to have 2 degree of freedom for this joint. Now coming to this joint again, ideally it is 3. But due to this vertical reaction here, there will be no degree of freedom in the y direction. So again, degree of freedom for this joint is 2. For this fixed support, you can see this. If this is a rigid joint, the degree of freedom is 3. But due to this vertical reaction, there will be no vertical displacement. Due to horizontal reaction, there will be no horizontal displacement. And due to moment reaction, there will be no rotational displacement of this joint. So just count the total degree of freedom for the beam. So 2 here and 2 here. So degree of freedom for this beam, dk is equal to 4. Dk for this beam is equal to 4, right? So this is how you need to do it. Please go for this one. It's a pin jointed plane frame. It's a pin jointed plane frame. So the degree of kinematic indeterminacy for the truss is nothing but a pin jointed plane frame, right? For a pin joint in plane frame, for a pin joint in 2D, simply, what is the degree of freedom for a pin joint in 2D? For a pin joint in 2D, can anybody tell me what is the degree of freedom? For example, this is a pin joint in 2D. What is the degree of freedom for a pin joint in 2D? Anyone? For a pin joint in 2D, what is the degree of freedom? Can anybody tell me this answer? For a pin joint in 2D, what is the degree of freedom here? Anyone with any answer here? For a pin joint in 2D, the degree of freedom is 2. For every joint, the degree of freedom is 2. That is delta x and delta y. For every joint, there are 2 degrees of freedom, delta x and delta y. Okay, sir. Now calculate the degree of kinematic indeterminacy for this truss. So again, you need to go joint by joint. So for this joint, degree of freedom is 2, delta x and delta y. For this joint again, degree of freedom is 2, delta x and delta y. For this joint again, the degree of freedom is 2, delta x and delta y. For this joint, ideally it should be 2, delta x and delta y. But due to this vertical reaction, there will be no delta y. Again for this joint, ideally it should be 2, delta x and delta y. But again due to this vertical reaction here, there will be no delta y. For this joint, ideally it should be 2, delta x and delta y. But due to these two support reactions in vertical and horizontal direction, there will be no degree of freedom for this joint. Always go with this arrow method because this will going to give you the most correct answers. So please count the degree of freedom. So 1, 2, 3, 4, 5, 6. Then you have 7 and 8. The total degree of freedom for this structure is equal to 8. Dk for this truss is 8. Any one of you are getting some other answers? Anyone who is getting some other answer for degree of freedom? Anyone who is getting some other answer for degree of freedom? So 2, 4, 6, 6 plus 1, 7, 7 plus 1, 8. Okay, like this you need to solve for pin jointed plane frame. Let's move ahead with the next question. Now you need to find out the degree of kinematic indeterminacy for the frame shown below. I told you this. For a rigid joint in 2D, the degree of freedom for every joint is 3. For a rigid joint in 2D, for a rigid joint in 2D, for a rigid joint in 2D, what is the degree of freedom? For example, this is a rigid joint in 2D. So the degree of freedom will be 1 delta x, another one will be delta y, and third one will be the rotation of the joint, that is theta z. So for every joint, the degree of freedom associated is 3. You have to move joint by joint and find out the degree of freedom for this structure. Okay, chalo do this, have 1 minute of time. Since this structure also contains a hybrid joint, therefore it will be interesting from your end to analyze this. Go for it. 1 minute of time for you. Please go for it. Go for it, go for it. Go for it. Calculate the degree of kinematic indeterminacy for this rigid jointed plane frame. Okay, let's check this out. This is my first rigid joint. For this rigid joint, you have delta x, delta y and theta z. So degree of freedom for this rigid joint is 3. Now coming to this hybrid joint, the degree of freedom is 4. Now check out what are those 4 degree of freedom. This member will undergo independent deflection, independent deformation. This portion will also undergo independent deformation. So this is delta x1, this is delta x2. Then this joint will undergo vertical deflection and this joint will undergo rotational deflection like this. So this is how you have 4 degree of freedom for this axial shear hinge. Now coming to this internal hinge, due to this internal hinge, this member can undergo independent rotation and this member can also undergo independent rotation. Then this joint can undergo delta x and delta y. So in total, you have 4 degree of freedom over this internal hinge. Now coming to this rigid joint, for this rigid joint you have delta x, delta y and theta z like this. Now coming to this fixed support, okay, ideally for this rigid joint there has to be delta x, delta y and theta z. But due to the support reactions offered by the fixed support in the vertical direction, there will be no degree of freedom in the vertical direction. Due to this horizontal reaction, there will be no displacement in the horizontal direction. And due to this moment reaction here, there will be no rotational displacement also. Coming to this hinge support, ideally for this hybrid joint, there has to be 3 degree of freedom. Okay. But due to this hinge support, there will be 2 support reactions. Vertical support reaction will not allow vertical deflection. Horizontal support reaction will not allow horizontal deflection. So this joint will only have 1 degree of freedom and that is the rotational deflection. Now coming to this roller support only offers 1 support reaction and that support reaction will not allow the deflection in the vertical direction. So this will be not allowed. Now just count the degree of freedom. So you have 0 here, 3 here, 3 plus 4 is 7. Okay. This joint is also having 3 degree of freedom, 1, 2 and 3. So 3 plus 4 is 7, 7 plus 3 is 10, 10 plus 4 is 14, 14 plus 3 is 17, 17 plus 2 is 19 and 19 plus 1 is 20. So degree of freedom for this structure, dk is equal to 20. dk is equal to 20 and this is when the members are extensible. Okay. All of you are getting the same answer or any other answer you are getting? Just quickly confirm it once. Are you getting the same answer or you are getting some other answer? Are you getting the same answer or some other answer you are getting here? Kindly confirm it once. Let's move ahead with this next. This is another portal frame given to you and you need to find out the degree of freedom. Okay, check this out. For this rigid joint, the degree of freedom will be 1, 2 and 3. For this rigid joint, the degree of freedom will be 1, 2 and 3. For this rigid joint, there will be 1, 2 and 3 degree of freedom. Now coming to this rigid joint, again you have 1, 2 and 3 degree of freedom. For this internal hinge, you have 1, 2 and then you have delta x and delta y. So degree of freedom here is 4. For this rigid joint, you have 1, 2 and 3 degree of freedom. For this internal hinge, observe this. This member can undergo independent rotation. This member can undergo independent rotation and this member can undergo independent rotation. So you have 3. Then this joint can undergo delta x and delta y. Okay. So in total you have 5 degrees of freedom here. I told you, whenever n number of members are connected through the internal hinge, the degree of freedom will be n plus 2. 3 members are connected. So what is the degree of freedom of this internal hinge? 3 plus 2, that is 5. And that is how we will going to show these 5 degree of freedom. Ideally, this rigid joint should have 1, 2 and 3 degree of freedom. But due to this vertical reaction, there will be no vertical deflection. Horizontal reaction will not allow any horizontal deflection. And this moment reaction will not allow any rotational deflection here. Coming to this joint, ideally it should have 1, 2 and 3 degree of freedom. But due to the vertical support reaction, there will be no vertical deflection. Due to horizontal support reaction, there will be no horizontal deflection. Again coming here, you have 1, 2 and 3 degree of freedom, but ideally it should be like 3, but this vertical support reaction will not allow the vertical deflection, horizontal support reaction will not allow horizontal deflection, and this moment reaction will not allow this rotational deflection. Okay. So you can calculate very good, Avinash. Avinash has said 25. Let's check this out. So 0 here, then 5 here. 5 plus 3 is 8. 8 plus 3 is 11. 11 plus 3 is 14. 14 plus 1 is 15. 15 plus 0 is 15. Then 15 plus 3 is 18. 18 plus 4. 18 plus 4 is 22. And 22 plus 3 is 25. Absolutely correct answer, Avinash sir. The degree of static indeterminacy for this portal frame is equal to 25. Absolutely correct answer. Absolutely correct. Let's move ahead to the next question. This is again a portal frame given to you. You need to find out the degree of kinematic indeterminacy. Go for it. But this time you have to neglect the axial deformation, means the members are axially rigid. Check this out. Okay, I'll start from here. First of all, this is a rigid joint. Ideally, it should have 1, 2 and 3 degree of freedom. But vertical reaction here will not allow vertical deflection. Horizontal reaction will not allow horizontal deflection. And this moment reaction will not allow this rotational deflection. Coming to this joint, ideally it should have 1, 2 and 3 rotational, right? But since this member is axially rigid, so there will be no vertical deflection of this joint. There will be one sway and one rotational deflection here. Now again coming here at this joint, ideally it should be 1, 2 and 3. But since this member is axially rigid, so there will be no vertical deflection of this joint, only there will be a sway and a rotational deformation at this joint. Now coming to this joint, ideally it should be 1, 2 and 3 degree of freedom, but since this member is axially rigid, so it will not allow any axial deformation. This member is axially rigid, so this will not allow any vertical deflection at this joint. Now coming to this joint should be practically having 3 degree of freedom like this, 1, 2 and 3. But since this member is axially rigid, so it will not allow any axial deflection. This member and this member is axially rigid, so it will not allow any vertical deflection. Now coming to this joint, practically this joint should have 1, 2 and 3 degree of freedom, but because of this hinge support, these two support reaction in vertical and horizontal direction will not allow the deflection in horizontal and vertical direction. So only 1 degree of freedom exists here for this for this hinge support. Now coming to this fixed support, practically it should be 1, 2 and 3, but due to the support reaction at fixed support like this, vertical, horizontal and the moment reaction will not allow vertical, horizontal and moment or rotational deflection over this fixed support. Now coming to this joint, practically it should be 1, 2 and 3 degree of freedom like this, okay. But since this member is axially rigid, so it will not allow any axial deflection. This member is axially rigid, so it will not allow any vertical deflection. Only there will be one rotational deflection of this joint. Now coming to this joint should also have 1, 2 and 3 degree of freedom like this. But since this member is axially rigid, so there will be no horizontal deflection. This member is axially rigid, so there will be no vertical deflection. Only one rotational deflection will be existing. Now coming to this free end. This free end again can have 3 degree of freedom, horizontal, vertical and then rotational deflection. But since this member is axially rigid, so it will not allow any axial deflection. So degree of freedom for this free end is only 2. Now just count the total degree of freedom. So you have 0 here, 2 here, 2 plus 2 4, then 4 plus 1 5, plus 1 6, plus 1 7, and then 7 plus 1 8, 8 plus 1 9 and 9 plus 2 11. Are you getting the same answer for this? Are you getting degree of kinematic indeterminacy for this frame as 11? Just quickly comment. Just tell me yes or no. Are you getting the same answer or you are getting some other answers? Please quickly comment here. So is it 11? This will be 0. This will be 2, 2 plus 2, 4, 4 plus 1, 5, 5 plus 1, 6, 6 plus 1, 7, 7 plus 0 is 7, 7 plus 1 is 8, 8 plus 1 is 9, and 9 plus 2 is 11. Are you getting the same answer or some other answer? Please tell me, are you getting the same answer or some other answer for this? Degree of kinematic indeterminacy. Now I would like to tell you one thing. These two horizontal deflections, why I have taken? Because these two horizontal deflection is because of the sway of the portal frame, right? It has nothing to do with the members are axially rigid or not. The sway of the portal frame can be restricted if you have any diagonal member. If any diagonal member is present, then that diagonal member will not allow the frame to sway. Okay. So if any diagonal member would have been present here, then I would have not considered this horizontal deflection as well. And that you should keep a check, because the next question which is coming up is a GATE 24 question, one of the most fantastic question that is framed from this topic till date. If you approach this question using the formulas, definitely you will get the incorrect answer. Definitely you will get the incorrect answer. But this is the portal frame which is given to you. For this portal frame, you need to find out the degree of kinematic indeterminacy. 1 minute of time for you. Go for it. Go for it. It's a GATE 24 question asked for 1 marks. I think it is 2 marks, not 1 marks. Go for it. Go for it. So this is the frame shown to you. Any answers? Prajat is saying 10. Okay, sir. Let's see this. Question says that the plane frame shown in the figure has fixed support at joint A, hinge support at joint F, and ruler support at joint I. In the figure, A to I indicate the joints of the frame. If the axial deformations are neglected, axial deformations neglected means members are axially rigid. Okay. For that, you need to find out the degree of freedom for this portal frame. Chalo, let's see this. We'll start from this fixed support. For this fixed support, ideally, if we treat this as a rigid joint, it should have 3 degrees of freedom. But because of this vertical and horizontal and moment reaction, there will be no degree of freedom for this fixed support. Now coming here, practically this rigid joint should have deflection in horizontal, vertical, and a rotational deflection like this. But since this member is axially rigid, so there will be no vertical deflection of this joint. And because of this diagonal bracing, there will be no sway of this portal frame. That is what I am trying to tell you. Because of this diagonal bracing, there will be no sway to this portal frame, right? There will be only one rotational deformation of this joint. Then coming to this joint practically should have horizontal deflection, vertical deflection, and one rotational deflection. But since this member is axially rigid, so there will be no vertical deflection. Because of the diagonal bracing, there will be no sway of this portal frame. So there will be only 1 degree of freedom for this joint. Now coming to this joint, there should be 1, 2 and 3 degree of freedom for this joint. But since this member is axially rigid, so there will be no axial deflection. Since this member is axially rigid, so there will be no vertical deflection. So there will be only one deflection, that is rotational deflection. Coming to this free end, so this free end practically should have 1, 2 and 3 degree of freedom. But since this member is axially rigid, so there will be no deflection in the horizontal direction of this free end. So degree of freedom for this free end is only 2. Now coming over this joint practically should have 3 degree of freedom, delta x, delta y and theta z. Okay. Because this member is axially rigid, so there will be no horizontal deflection. This member is axially rigid, so there will be no vertical deflection. So there will be only 1 degree of freedom, that is rotational. Coming to this joint should have practically 3, horizontal, vertical and rotational deflection. But since this is a hinge support, so the vertical reaction here will not allow vertical deflection. Horizontal reaction will not allow horizontal deflection. So there will be only 1 degree of freedom here. Coming here, so you have one support reaction here. Practically it should have 1, 2 and 3 degree of freedom. But check this out. This vertical reaction will not allow the vertical deflection. Since this member is axially rigid, so it will not allow any horizontal deflection also for this joint. So degree of freedom for this joint will be only one, that is rotational deflection. Now coming to this joint practically has 1, 2 and 3 degree of freedom, 1, 2 and 3. But since this member is axially rigid, so there will be no axial deflection or horizontal deflection. Since this member is axially rigid, so there will be no vertical deflection. So this is how you need to solve this question. Last year, most of the students who have applied the formula have got the wrong answers. And this is why I prefer this arrow method for calculating the degree of kinematic indeterminacy. Check this out. So 0 here, 1 here, 2 here, 3, 4, 5, 6, then 7 here, then 8 and then 9. So degree of kinematic indeterminacy for this structure is equal to 9. dk is equals to 9. Avinash sir has counted one extra, I guess. Prajat has counted one extra, sorry. Prajat, just check your answer, right? And you can have the correct solution for this question. So this is how you need to solve. What is the learning from here? Learning is whenever diagonal bracing is present in the portal frame, the portal frame will not going to sway. And you have to neglect the degree of kinematic indeterminacy due to sway of the portal frame. Okay, sir. Let's move ahead with the next thing. So here one beam is given to you. Now I think you can solve this. It's a GATE 2022 question. It's a very easy question. First of all, you need to find out the difference, or you need to find out the degree of static and kinematic indeterminacy for this beam shown to you. Please do this. It's a very easy question. I'm not giving you time for this. This is a beam, right? So what will be the degree of static indeterminacy? Degree of static indeterminacy for the beam is R minus 3. It's a general loading case because this force will going to give both horizontal and vertical reaction over this joint. So R is equals to 3 plus 2, 5. 5 minus 3 will be 2. So degree of static indeterminacy will be 2. What about degree of kinematic indeterminacy? Check this out. So for this hinge support, right, this should be treated as a rigid joint. For a rigid joint, the degree of freedom is 3, right? But because of this vertical and horizontal reaction at this support, there will be no vertical deflection and horizontal deflection of this joint. So there will be only rotational deflection. And again, because of the 3 support reaction for this fixed support, there will be no degree of freedom for this joint, right? So degree of freedom for this beam is just equal to 1. So simply ds is equals to 2, dk is equals to 1. That is the answer. It's a GATE 2022 question asked for 2 marks. Just see the level of question. Moving ahead with this next. Okay, so this covers the first topic, the first chapter, that is the degree of static and kinematic indeterminacy. Let me just move very quickly because I need to cover a lot of questions today. So the next is the analysis of the determinate truss. Basic things we know, I have just included this. Important thing is, for analyzing the truss, there are basically 3 methods. First one is called as the collinear theorem, where you identify the zero force member. It is not the complete method of analysis, but actually it reduces your calculation part. So whenever any truss comes to you, first thing is identify the zero force member. Now sir, how to identify the zero force members? So you have three basic conditions. First condition is, if two non-collinear members are meeting at a joint and no external load is acting, then force in both the member will be zero force. The second condition is, if three non-collinear members are meeting at a joint such that two of them are collinear and there is no external load acting over a joint. Let me draw this quickly. So first condition is, if two non-collinear members are meeting at a joint, if two non-collinear members are meeting at a joint like this, if two non-collinear members are meeting at a joint and no external load is acting over the joint, then force in both the member will be zero force. Second, if three members are meeting at a joint such that two members are collinear and no external load is acting, then force in the third member will be zero force. Next condition is, if two members are meeting at a joint such that the external load acting over a joint is in line with one of the members, then force in the other member will be zero force. So using these three basic conditions, you can identify zero force members. That reduces your calculations. Chalo, check this out. Here one truss is given to you. It's a GATE 2016 question. Please remember, you need to just find out which members do not carry any force. Means, what are the zero force member for this truss? Please do this. You have just 1 minute of time, go for it. I am giving you only 1 minute of time today. Go for it, because we have to see a lot of questions. Go for it and tell me the answer for this. How many members are zero force members here? Please find out the number of zero force members here. Please find out the number of zero force members here. Okay, let's see this. So always remember those three conditions that I told you for calculating the number of zero force member. Come to this joint. This joint has two support reactions. This joint has two support reactions like this. There will be two support reactions here, vertical and horizontal. So we cannot say anything about these two members. Now coming to this joint, no external load is acting and member EF and FG is in line. So force in the third member will be zero force. Now since this is a zero force member, so forget this member and come to this joint T. So when you come to this joint T, again TE and TS are in line. So force in this member TG will be a zero force. So wherever you have zero force member, you have to neglect it. Very good answer, Prajat. Let's see how many of them are zero force members. Now come to this joint H, right? Over this joint H, member GH and GJ, HG and HJ are in line. So force in the third member will be zero force. So this will be a zero force member here. Any other, when you come to this joint U, you have 1, 2, 3, 4 members. We cannot say anything. You come to this member G, so you have 1, 2, 3 and 4 members. Again, we cannot say anything. Okay, sir. Come to this member J, come to this joint, J. So there are 1, 2, 3, 4 members. We cannot say anything. Come to this joint R. So you have 1, 2, 3, 4 members. We cannot say anything. Come to here. This N has one vertical reaction, so we cannot say anything whether these two members are zero force or not. Then come to this joint M. Members ML and MN are in line, so force in the third member will be zero force. Now since this is a zero force member, so forget it. Come to this joint P. At this joint P, member PQ and PN are in line, so force in this third member will be zero force. Okay, sir. Now check this out and tell me, is there any other zero force member that you are finding? So you have 1, 2, 3, 4 and 5 zero force members that are present over this truss. So number of zero force members are 5. Number of zero force members are 5. Doesn't matter whether your answer is correct or incorrect. At least someone is answering. At least you should answer that. Keep answering, right? These sessions are conducted to rectify all your mistakes that you are doing while solving such easy questions. And these are like those questions ki if you miss out over these questions, eventually you start losing marks in the GATE examination. So we don't have to make silly mistakes in this easy segment of structural analysis. Okay, let's move ahead with this. This is the next truss given to you, and you need to find out forces in the member BE, BC and CD. So BE, BC and CD, right? You need to find out forces in the member. I just give you 2 minutes of time for it. Please tell me the answer for this. BE, BC and CD. BE, BC and CD. Go for it. Any answers? Chalo, check this out. First of all, you need to find out force in the member BE, BC and CD. So this is B, this is BE, this is BC and this is CD. Okay. Now one very interesting thing here is, so vertical length kya hai? Vertical length is not given, beta. Avinash, vertical length is not given. Prajat is saying CD is equals to P by 2. Absolutely correct answer, Prajat sir. Absolutely correct answer. So you can see here, this is the vertical reaction VC, right? And when you observe this joint, two members are meeting at a joint and external force acting is in line with one of the member. So force in this second member will be zero force. So force in this member BC, force in member BC is equal to 0. Force in member BC is equal to 0, right? BE is equals to P. Very good answer, Prajat. Very good. Now, for calculating this CD, force in the member CD, you need to find out the value of VC. So, for calculating VC, you stand at point A and write down summation of moment about A equal to 0. So, summation of moment about A equal to 0. So, the first moment will be due to this external load P. Value will be P into L by 2. It's a clockwise moment. So, P into L by 2. The second moment will be due to this VC. Value will be VC into L, and it's an anti-clockwise moment. So minus VC into L equal to 0. So the value of VC is equal to P by 2. Value of VC is equal to P by 2. Now what you need to do is, you need to stand at this joint C and you have to take the summation of vertical forces equal to 0. So considering joint C, considering joint C. So at joint C, you have force in the member CD. This is FCD. Force in the member CD. This is joint C, and this is vertical reaction VC. So what you can write down, summation of vertical forces equal to 0. So from here I can write down FCD is equal to VC, and we know that VC is equals to P by 2. So FCD is also equal to P by 2. FCD is also equal to P by 2. Okay, sir. So this is how we have calculated two member forces. Now coming to the third one, which is the most typical one. For that, I have to consider equilibrium of this joint E. Consider equilibrium of joint E. Considering equilibrium of joint E. So considering equilibrium of joint E. Check this out. So at this joint E, you have 1, 2 and 3 members meeting, right? Consider force in the member ED, EA and EB and assume those directions. So I am assuming directions like this. This is the external load P. This is the external load P. What I am doing here is very important, because it will going to you one more approach of solving a question. So these are the two member forces which are in line, and then you have this member force like this. This is FBE. Okay, so this is P, this is FEA, FED. This is P, this is FEA, this is FED, and this is FBE. Okay, so usually what are the equilibrium equations that we write? That summation of horizontal forces equal to 0, summation of vertical forces equal to 0. But do you know that you can write down equilibrium equation corresponding to any two mutually perpendicular axes? It need not to be necessarily along X or along Y. If the system is under the state of static equilibrium, means as per any frame of reference, it has to be under the state of equilibrium. Means usually what we have, usually we consider axis like this. This is my X axis, then this will be my vertical axis, Y axis, right? And what I do, I write down summation of horizontal forces, that is summation of force along XX axis equal to 0 and summation of force along YY axis equal to 0, right? So right now, if you write down the summation of vertical forces equal to 0 or summation of forces about YY equal to 0, then these two member forces will also come into play. This is theta and this is also theta, right? So right now these two components, so FED sin theta and FEA sin theta will also come into play. Now what I want here is, I will just twist my reference axis. I will keep my reference axis like this. This is my reference axis. This is my reference axis now. This will be my XX axis. This will be my XX axis, and perpendicular to this XX axis, this will be my YY axis, or I should write down YY dash. So this is X dash, and this is Y dash, Y dash. So what opportunity I got after switching my reference axis, that I can write down summation of forces along X dash equal to 0, and I can write down summation of forces along Y dash equal to 0. So if this angle is also theta and this angle is also theta, so I can write down summation of forces along Y dash equal to 0. So I have P cos theta acting towards down. So I will write down minus P cos theta, and then I have this FBE cos theta acting upwards. So I will write down plus FBE cos theta, FBE cos theta. The other two forces will not have any component in the perpendicular direction, so I have simply ignored them. So from here the value of FBE will be equal to P, and this is the only catch in this question for which I have considered this question in this gate score booster session, so that to give you an idea that as per your convenience you can also switch your reference axis, right? Reference axis is just a mode of making your analysis easy. For standardizing your analysis, you choose a reference axis, and that is totally in your hand. Okay, sir. Let's move ahead with this. This is a next question asked in the year 2024. Just look into the length of the question. Read the question properly. I am giving you 3 minutes of time. I want proper solution for this. Go for it. Go for it. All these distances are 1 meter. Go for it. It's a gate 24 question. It's a very, very fantastic question. Question says that a plain truss shown in the figure has 13 joints, 22 members. The truss is made of homogeneous prismatic linearly elastic material. All the members have identical axial rigidity to A to M. Indicates the joint of the truss. The truss has a pin support at joint A and L and roller support at joint K. The truss is subjected to a 10 kN load vertically downward force at joint H and a 10 kN horizontal force in the rightward direction at joint B as shown. Now see this. Intentionally they have written to waste your time. They could have directly given you the question, and they could have written axial rigidity is constant for all the members. Intentionally, they want you to waste your time here and get confused, right? Our important point is this truss, okay? The truss is given to you. This is joint L. They are asking what is the magnitude of the reaction at the pin support L. At this hinge joint, sorry, at this hinge support, you need to find out the reaction here. Okay, let's do this. So you have 1, 2, and you have this third block here. So you have a hinge support, and a roller support. Okay, let me just apply the load. So you have 10 kilonewton here and 10 kilonewton there. So A, B, C, D. This is A, B, C, D. And then you have E, F, I, E, F, G, H, I. So this is 2 meter, this is 1 meter, and I think this is also 1 meter, 1 meter, 1 meter, and this is 2 meter. Okay, now another set of dimensions are also given like this. 1 meter each. So basically these are the dimensions of the trusses that is given to you, right? For this truss, you need to find out the support reaction at L. This year when the student has seen the question, they said ki sir, 1, 2, 3, 4, 5 support reactions are there and we have only 3 equilibrium equation. Is it really possible to determine 5 support reaction using these 3 equilibrium equations? Check this out. What we will going to do is, first, we will cut this truss. Now you have to visualize, right? Every time I cannot draw the diagram, it is a complicated diagram. So what I will do is, first I will consider one section XX and cut these 2 members. This is my section 11 and using this section 11 I am cutting these 2 members. Using this section 11 I am cutting these 2 members. This is my section 11. This is section 11. Using this section 11, I will cut the truss from here and I'll stand at this D and write down summation of moment about this left of section 11 equal to 0. Means simply I have cut this truss using section 11 and I am considering equilibrium of left of section 11. So at A you have 2 support reactions. You have VA and HA. This is VA. And horizontal reaction here is HA. So first thing here is considering equilibrium of left of section 11. Considering equilibrium of left of section 11. So you have to cut this truss using this section 11 and consider equilibrium of the left side. You stand at this point D and write down summation of moment about D equal to 0. So summation of moment about D equal to 0. So when you write down summation of moment about D equal to 0, this 10 kilonewton load will not going to give any moment. You will going to have one clockwise moment due to VA, value will be VA into 2. Then you have this anti-clockwise moment due to HA, value will be HA into 2 again. This from here to here the distance is 2 meter. So you have VA into 2 minus HA into 2. So from here you got one relation, that is VA is equal to HA. VA is equal to HA. This is the first relation you got. Now I tell you how to get the second relation. Consider one section here. This is my section 22 and this time I'm cutting these 2 members using section 22. This is my section 22 and using this section 22 I'm cutting 2 members. What are those 2 members? Member JG and JH I am cutting using section 22. So first I will stand at this joint J and I will write down the summation of moment about J equal to 0 for the right of section 22. So here on the right of section 22, here you have one horizontal reaction HK. Then you have one vertical reaction here VL and then you have here horizontal reaction HL like this, right? So considering equilibrium of right of section 22 and writing summation of moment about point J equal to 0. So considering equilibrium of right of 22 and writing summation of moment about J equal to 0. So when you write down summation of moment about J equal to 0, this HK and this VL will not going to give any moment. You will going to have one anti-clockwise moment due to HL. Value will be HL into 2 and it's an anti-clockwise moment. So I will write down minus HL into 2 equal to 0. So from here the value of HL will be equal to 0. the value of HL will be equal to 0. So HL came out to be 0. Now next, sir, consider equilibrium of left of section 2 and again about point J, write down summation of moment about J for left of section 2 equal to 0. So considering equilibrium of left of section 2, considering equilibrium of left of section 2 and writing summation of moment about J equal to 0. Now this time you have to stand at this point J and you have to consider left of section 2. So the first anti-clockwise moment due to this 10 kN load value will be 10 into 1. So minus 10 into 1. The second moment will be due to this VA and the value will be VA into this distance. So what is this total distance? 2 plus 2, 4 plus 2, 6. So VA into 6 will be a clockwise moment about J. So plus VA into 6. The third moment will be due to this HA and this HA will going to give you the anti-clockwise moment value will be HA into 2 about point J. So minus HA into 2 equal to 0. Please calculate this. So you have 6 VA minus 2 HA is equal to 10. Initially we have derived this VA is equals to HA. So substitute HA is equals to VA from here. So you have 6 VA minus 2 VA is equal to 0. So you have 4 VA equal to 0. Sorry, 4 VA is equals, why it is 0? This is 10. So 4 VA is equals to 10. So the value of VA is equal to 2.5 kilonewton. Value of VA is equals to 2.5 kilonewton, right? This is the value of VA. Now next what you can do is you can take summation of vertical forces equal to 0 for the entire truss. For this entire truss, you can take summation of vertical forces equal to 0. So what will be the value of vertical forces? So you have VA acting upwards, VL acting upwards and 10 kilonewton acting downwards. So if I write down for complete truss, summation of vertical forces equal to 0. So you have VA acting upwards plus VL acting upwards minus 10 kilonewton acting downward equal to 0. So VA you have already calculated as 2.5 plus VL minus 10 is equal to 0. So the value of VL is equal to 7.5 kilonewton. This is 7.5 kilonewton. They are asking you only one support reaction. But what if we can calculate all the support reaction? We can calculate everything now. We already know the value of HL. What is HL? HL is equals to 0. We also know the value of HA. HA is also equal to 2.5 because HA is equals to VA. So HA is also equal to 2.5. It is also equal to 2.5 kilonewton. So where I have assumed the direction of HA, I have assumed HA like this and HK is acting this side, right? So I can write down summation of horizontal forces equal to 0 in the complete truss to calculate the value of HK. So summation of horizontal forces equal to 0. So 10 kilonewton is acting towards right. Then you have HA acting towards right. Then you have HL. So HL is already equal to 0 minus HK. This is equal to 0. So check this out. So you have 10 plus 2.5. HL is 0 and minus HK is equal to 0. So what is the value of HK from here? So HK is equal to 12.5 kilonewton. So not just any one support reaction, we have calculated all the support reaction for the given truss. So from here, what is the learning? The learning is never judge a truss by the number of support reaction. Use your brain and think how we can analyze the truss for finding out the support reaction, right? And method of section is one of the easiest method to find out this member forces and support reactions for these type of trusses. In the same way, we have one more question. It's a GATE 2022 question. It's a similar variety. This is for you, right? You can take the screenshot. I'll be giving you the PDF where this question is there. You can try this question by your own. Okay. Let's move ahead with this. Next, one of the most common variety of question, a tower is given to you. And for this tower, what they are asking force in this member XW. They are asking what is the force in this member XW. So whenever you have these type of tower type of questions, always remember that you have to consider a section which should cut 4 members. And out of these 4 members, 2 should be collinear members. Whenever you have a tower type of a question, always remember one thing, that you have to cut 4 members using the section, and out of those 4 members, 2 should be collinear members. So right now they are wanting this member force XW. So what I will do, I will cut this tower like this. Check this out. I will cut the tower like this. This is 1, this is 2. So you have this 10 kilonewton, you have this 10 kilonewton, and you have this 10 kilonewton. This is a hinge support. This is also a hinge support. So this is PQRS. This is TUV, this is WXYZ. Okay. Most of the tower questions that we have seen over the years is solved using this method. Means whenever you have the tower questions, there are 99% chances that you won't even require the support reactions. Okay. They are asking you to find out the value of this member force. So what you need to do is, you need to take section like this. This is my section which is cutting 4 members. This is the section XX which is cutting 4 members. You can see this. This is a section cutting 4 members, and out of these 4 members, 2 members are collinear. So like that you have to cut and take the section. So I will consider the equilibrium of upper part of section XX. So considering equilibrium of upper part of section XX. Considering equilibrium of upper part of section XX, right? So you have one triangle like that. Chalo, let me draw the exposed forces here. So you can see this. This member forces will be exposed after cutting the section. This member force, and this member force will be exposed. So let me draw all these member forces. So this is the first exposed member force. The first exposed member force, then this is the second exposed member force, next exposed member force, and then you have this next exposed member force. So these are the 4 exposed member forces. You have 10, 10, 10 acting like this. So this is 10 kilonewton. Again this is 10 kilonewton. And again this one is also 10 kilonewton. This is force in the member PQ. This is force in the member QT. This is force in the member XT, and this is force in the member XW, right? So this is QRS TUV WXY. X, Y, Z, okay. This distance is how much? This is given to you as 444 meter, and this total distance is also 4 meter. So this is 4 meter, this is 4 meter, and this distance is also 4 meter. So simply what you need to do is, after considering the upper part, right, is stand at Q and write down summation of moment equal to 0. So moment due to these 3 other member forces will become 0, and you have only one unknown member forces, that is Fxw. So just write down summation of moment about Q equal to 0. So I'll start like this. When I stand at Q, there will be no moment due to Fpq, Fqt, and there will be no moment due to Fxt. There will be first clockwise moment due to this 10 kilonewton load, then again a clockwise moment due to this 10 kilonewton load. So first 10 kilonewton load will give you the moment of 10 into 4. Second 10 kilonewton load will give you the moment of 10 into 8. Okay. And then you have this member force which will going to give you the anti-clockwise moment. Value will be Fxw into 4. So I will write down minus Fxw into 4 equal to 0. Get me the value of Fxw from here. So Fxw will be how much? This will be 10 plus 20. So Fxw will be 30 kilonewton. Fxw will be equal to 30 kilonewton. All of you just quickly confirm, are you getting the same answer for Fxw? Kindly confirm this. Fxw, are you getting the same answer, 30 kilonewton? Please confirm this. For Fxw, are you getting the same answer of 30 kilonewton? Please confirm it. Okay. So like this, you need to solve the tower variety of question where you have to take the section cutting 4 members, out of them 2 should be collinear. Okay, sir. Let's move ahead with this. Okay. So like this, you can solve the questions which are asked from the trusses. Basically, for analyzing the trusses, you have 3 methods. First one is the collinear theorem where you identify the 0 force members. Second one is the method of joints, and third one is the method of sections. Okay. Next you have, for analyzing the structures, you have 2 different methods, force methods and the displacement methods. What do we mean by analyzing the structure? Analyzing the structure simply means to calculate the unknown forces and unknown deformations. Now sir, if unknown forces are less, so first we will calculate those unknown forces and then we will calculate the unknown deformations. In the same note, if unknown deformations are less, then first we calculate unknown deformations and then we go for calculating the unknown forces. Based on this analysis, we decide which method to choose. If unknown forces are less, then we go with the force method of analysis. So if unknown forces are less, what is a measure of unknown forces? Degree of static indeterminacy. So if degree of static indeterminacy is less than the degree of kinematic indeterminacy, then the method of analysis that we choose are the force methods. If degree of kinematic indeterminacy is less than the degree of static indeterminacy, then we go with the displacement methods of analysis. I think I have also listed down all the methods. So these are the methods of analysis. In force method, we have method of consistent deformation, strain energy theorem, flexibility matrix method, columns analogy, three moment method, and also the principle of superposition. In the displacement of method of analysis, we have slope deflection method, moment distribution method, stiffness matrix method, and Canny's rotation method. You can use any of them for analyzing any structure. Let's move ahead with this. One structure is given to you, one beam is given to you, and they are asking which method of analysis should they follow. Go for it. Go for it. I am just giving you 1 minute of time. Go for it. So take 2 minutes of time because you have to do two calculations. How you will decide whether force method or displacement method? Calculate degree of static indeterminacy, degree of kinematic indeterminacy, and then make a decision. Please go for it. Any answers? Which method we should use here? Degree of static. Arey, very good answer, Prajat. Very good. Let's see this. Let's see whether you have answered this correctly or not. The question says that out of force method or displacement method, which method we should use? So first calculate the degree of static indeterminacy. So degree of static indeterminacy for this beam is R minus S. R is the number of support reaction and S is the number of equilibrium equation. Now check this out. For this beam, all the loadings are happening in the vertical plane or in the vertical direction. So it is a vertical loading case. In vertical loading case, for calculating the degree of static indeterminacy, horizontal reactions and horizontal equilibrium equations are not counted. So here, how many support reactions you have? You have one and a moment reaction here. You have one more support reaction here, and you have one and two support reaction here. So in total, 2 plus 1, 3 plus 1, 2, 5. Number of support reactions are 5 and number of equilibrium equations will be 2 because horizontal reaction is not counted. It's a vertical loading case. So ds is equals to 3. Now coming to dk. dk is equals to, okay, 2j minus r. So simply count the number of joints. 1, 2, 3 joints. So dk is equals to 3j minus r. For every joint 3, 3j minus r is the value of degree of freedom here. So number of joints are 3 and number of support reaction. Now here when you count the number of support reaction, you have to count all the support reaction. Even if it is a vertical loading case, you have to count all the support reactions here. So the total number of support reactions will be 3 plus 2, 5 and 5 plus 3, 8. 5 plus 3, 8. So in total 8 support reaction. dk is equals to 1. Since dk is less than ds, therefore we go with the displacement method of analysis. So Prajat sir has absolutely answered it correctly. Chalo, moving ahead with this next. A question is given to you. This is the question from the method of consistent deformation. Question says that a two span continuous beam having equal spans each of length L is subjected to a uniformly distributed load W per unit length. The beam has constant flexural rigidity EI. The reaction at the middle support is. A beam is given to you like this. A beam is given to you like this. And this beam is subjected to UDL. This is subjected to UDL of intensity W kilonewton per meter. Okay, this length is L and this length is also L. This is A, B and C. Flexural rigidity for member AB is EI and flexural rigidity for member BC is also EI. Now what they are asking is, they are asking you to find out the value of support reaction at B. Calculate support reaction at B. Calculate this support reaction at B. Just 1 minute of time for this easy question. If this type of question will come, it will totally depend how you are clicking these questions. Yes, thank you so much, Richa ma'am. Thank you so much. Please answer the question. So this is the question of to be solved by method of consistent deformation. What is the special thing about method of consistent deformation? That it can be only applicable to those structures for which the degree of static indeterminacy is 1. So this is a question which can be solved using method of consistent deformation, and it can be only solved, reason is the degree of static indeterminacy for this structure is 1. Now what you need to do is, whichever support reaction you want, you have to consider that as a redundant and you have to release it. Consider the support reaction at B as a redundant and release it. So this is the support reaction at B. So this is VB. This is VC. And this is your VA and HA. So consider the support reaction at VB as a redundant and release it. So considering VB as redundant, so you are left with this beam. Now simply tell me one thing, if this is a beam of length 2L, this is the beam of length 2L and the UDL intensity is W kilonewton per meter, what is the vertical deflection at B? What will be the vertical downward deflection at B? This beam will going to deflect like this. What will be this delta B? This length is L and this length is also L. Can anybody tell me what will be the vertical downward deflection delta B only due to this UDL? So vertical downward deflection delta B, I will going to use the standard result. It is W into L raised to the power 4. So L here is 2L. Total length of the beam is 2L. So W L raised to the power 4. Actually it is 5 upon 384. W L raised to the power 4. So L is 2L upon EI. Please simplify this and tell me the answer in simple form. 2 raised to the power 4 divided by 384. Just tell me the answer after like simplifying this. Please simplify this and tell me the answer. upon 384. So I will write like this. Delta B is equal to 80 upon 384 WL raised to power 4 upon EI. Okay, so this is the vertical deflection at B after releasing the redundant reaction VB. Okay, sir. Now the next step is only apply the redundant force and calculate the deflection at this point B. Next is only consider the redundant reaction and calculate the deflection at this point B. So this is VB, redundant reaction, and due to this BB, the beam will going to deflect like this. Calculate this delta B dash. This length is L, this length is also L. This is A, B and C. So what will be delta B dash? Use the standard result. Delta B dash is WL cube, means VB into 2L cube upon 48 EI. WL cube upon 48 EI is the vertical deflection, is the central deflection for a simply supported beam. Avinash is answering 5 WL by 4. Great answer, sir. Great answer. So this is equals to delta B dash is equal to, this is 8. 8 upon 48 is 6. So VB L cube upon 6 EI. Now what you need to do is, when you observe the final beam, when you observe this initial beam, what is the net deflection at B? Net deflection at B is equal to 0. Means whatever downward deflection is caused by UDL should be equal to the upward deflection caused by this redundant reaction. Okay. So this is the method of consistent deformation, that you apply the compatibility equation after finding out the deformations. So what I will write is, downward deflection by UDL should be equal to the upward deflection by this point load. Means delta B should be equal to delta B dash. So this is 80 upon 384 WL raised to power 4 upon EI should be equal to VB into L cube upon 6 EI. So this EI will cancel out, then L cube will cancel out. So you have VB is equal to 80 into 6 by 384 into WL. Please calculate this and tell me the answer. Are you getting the same? 5 WL by 4. So this is 80 into 6 by 384. Please calculate this. 80 into 6 by 384. Yeah. So VB is equals to 1.25 WL. So VB is equals to 1.25 WL. That is the same answer, 5 WL by 4. Absolutely correct. Okay. So like this, you need to apply the method of consistent deformation, where you need to release the redundant reaction, and after that you have to apply the compatibility equation, right, after writing down the deformations. Let's move ahead here. Try this next question. The next question says that a 2-span continuous beam, I think it is the same question. Okay. Next, try this question. It's a very good question. The question is asking, in a probed cantilever beam carrying a uniformly distributed load of W Newton per meter shown below, the reaction of the support B is. In the question, they are asking you to find out the support reaction B, but I want all the support reaction. Go for it. Go for it. Go for it. This is a question which is from the method, from the principle of superposition. Please go for it. Do it, do it, do it. Arey. Please go for it. Please go for it. It's a question from the principle of superposition. Please go for it. Option B. Very good. Find out other support reactions as well. Chalo, let's see this question. So the question says that you have a propped cantilever beam subjected to UDL. You need to find out all the support reaction in simple words. Let's do this question. So usually when you have a propped cantilever beam, always remember the principle of superposition. This is a propped cantilever beam. This is one vertical reaction VB here. Then you have this fixed support, and then this beam is subjected to UDL like this. The length of the beam is L. Intensity of loading is W kilonewton per meter. Just by observing the beam, can you say that delta at B is equal to 0? Just by observing the beam, can we say that delta at B equal to 0? Now sir, if delta at B is 0, there are these two forces whose combined effect of deformation at B is 0. Means first, if I only consider UDL removing this point load, if I only consider this UDL removing the point load, this UDL has a tendency to deflect this point B downwards like this. Okay. So this is delta B1, and this delta B1 is nothing but deflection due to UDL of this point B. And what is the value of delta B1? Delta B1 is nothing but the standard result, which is minus WL raised to power 4 upon ATI. Instead of using minus plus, I will just write down the magnitude, right? Without creating any confusion, I am only writing the magnitude. So delta B1 is WL raised to power 4 upon ATI. Now only consider this point load. This point load will try to deflect the beam upwards. This point load will try to deflect the beam upwards. This is VB, right? And under the action of VB, the beam will going to deflect upwards. And this is delta B2. Now sir, what will be the value of delta B2? Delta B2 is WL cube upon 3EI. Instead of W, you should write down VB. So this will be VBL cube upon 3EI. Standard results directly we know, right? So you have to simply equate delta B1 is equals to delta B2, then only delta B is equal to 0. So I will write down delta B1 is equal to delta B2. What is the value of delta B1? Delta B1 is WL raised to power 4 upon ATI. WL raised to power 4 upon ATI is equal to delta B2, which is VB into L cube. VB into L cube upon 3 EI. So from here the value of VB is 3 by 8 WL. So the value of VB you have calculated 3 by 8 WL. This is the question, it is solved, right? Very good answer, Avinash sir, very good answer. So VB is equals to 3 by 8 of WL. Now I want other support reactions also. I want the value of VA, I want the value of HA, and I want the value of MA. So what I can do is, for calculating VA, I will write down summation of vertical forces equal to 0. So when I write down summation of vertical forces equal to 0, VA is acting upwards, VB is acting upwards, and your UDL is acting downward, which is minus W into L. Substitute the value of VB. So VA is equals to W into L is the UDL minus 3 by 8 of WL. That is VB. Calculate VA. VA will come out as 5 by 8 of WL. VA will come out as 5 by 8 of WL, and once you got the value of VA, now you need to find out the value of MA. For calculating MA, stand at A and write down summation of moment about A equal to 0. So when you write down summation of moment about A equal to 0, the first moment will be minus MA, anti-clockwise minus MA. There will be no moment due to these two loads. Then this UDL will going to give the clockwise moment. Value will be plus W into L is the load into L by 2 is the lever arm. And then you will have the anti-clockwise moment due to VB. Value will be VB into L. So I will write down minus VB into L equal to 0. So from here the value of MA is equal to, so this will be WL square upon 2, WL square upon 2 minus VB is 3 by 8 of WL. So this will be 3 by 8 of WL square. Please calculate this. So this will be 4 minus 3, 1. So WL square upon 8 is the answer for MA. Are you getting MA as WL square upon 8? Just confirm this. Is this WL square upon 8? Quickly confirm this. Are you getting MA as WL square upon 8? Very good. Correct answer. Chalo. So this is how you need to deal with the cantilever beam, right? Most of the time we have seen this question. Strength of material also, for a strength of material, what they will do? In this propped cantilever beam, they will keep one internal hinge. And for structural analysis, they will keep you this propped cantilever beam directly, right? And they can ask you any support reaction, like one of the favorite variety of question that is asked from this segment. Let's move ahead with this. Next you have this. It's a very good question. What they are saying is, they want the distance of point of contraflexure from your end A. From your end A, they are asking you to find out the distance of point of contraflexure. What is the point of contraflexure? Point of contraflexure is that point where bending moment changes its sign. Okay, where bending moment changes its sign. Take 3 minutes of time. It's a fantastic question to solve. Go for it, and I want correct answers. I want correct calculations, because correct calculations will eventually get you the correct answers. Please go for it. Go for it, go for it. Please go for it. Go for it, go for it. Keep solving the question instead of throwing hearts. Please solve the question. Now sir, how to deal with this question? First of all, for solving this question, you need to plot the bending moment diagram. For calculating the bending moment diagram, you require the support reactions, right? So first thing is, first calculate the support reaction. This total length is 1 meter and from A to B, the length is 0.75 meter. Let's calculate the support reaction. Definitely a lot of learning you will going to have after solving this question. So stay with me and solve this question properly. So this is the beam given to us. It's a roller support here. And this beam is subjected to a point load of 10 kilonewton here. This is 0.75 L. So what I should write? This will be 3L by 4 and this is L by 4. Okay, sir. Say this is point A, this is point B and this is point C. Step 1 is you need to find out the support reaction. Now sir, any idea how to calculate support reactions here? Can anybody suggest me after observing this beam, how can I calculate the value of support reactions? Anyone? Can anybody tell me how to find out the value of support reactions here? Just like we did in the previous question, can we apply the same method? Answer is yes, you can apply the same method. But what you need to do is transfer this load from point C to point B. Transfer this load from point C to point B and consider only AB, right? So when you transfer this load from point C to point B, this beam will be like this. So when you transfer this load, there will be one downward load of 10. There will be one downward load of 10. This is not L, this is 1. So this is 3 by 4 and this will be 1 by 4. And then there will be a moment whose value will be 1 by 4 into 10, that is 2.5 kilonewton meter. Okay. So at this point B, a downward point load and a moment and one vertical reaction is acting here. So one vertical reaction VB is acting here. Check this out. One vertical reaction is acting here. This is A, this is B. What is delta at B? Delta at B is 0. Delta at B is 0. And now what is delta at B? Delta at B is nothing but the sum of delta B due to 10, delta B due to 2.5 and delta B due to this VB. So I will write down delta B is the sum of delta B1 plus delta B2 plus delta B3. Means independently, if you consider these loads and if you take the sum of the deformations caused by this load at point B, the sum will be equal to 0. If this equation is hard to visualize, you can simply try this. First, only consider this 10 kilonewton load. First, only consider this 10 kilonewton load, and due to this 10 kilonewton load, the beam will going to deflect like this. This is delta B1, right? And delta B1 is negative. What will be the value of delta B1? Delta B1 is equal to W L cube. What is L? L is 3 by 4. WL cube upon 3EI. This is delta B1. WL cube upon 3I, and it is negative, downward. So I will write down minus. Next is this moment. Next is only moment. This moment is 2.5 kilonewton meter. Now again, this moment will going to deflect the beam like this, and this is delta B2. Delta B2 is also negative, and the value of delta B2 is equal to minus ml upon EI. So m is 2.5, L is 3 by 4 upon EI. Sorry, ml square upon 2EI. So this is ml square upon 2EI. So minus 2.5 into 3 by 4 raised the power 2 upon 2EI. This is delta B2. Now this VB will going to deflect the beam upwards. So now only draw VB. Now only draw VB. This VB will going to deflect the beam upwards. And this upward deflection will cause this delta B3. And delta B3 is positive. And the value of this delta B3 is equal to, calculate this. So this will be equal to VB into L cube. So 3 by 4 cube upon 3EI. Take care of plus and minus sign, take the sum and get me the value of VB first. So delta B is equal to delta B1 plus delta B2 plus delta B3 equal to 0. So what is the value of delta B1? Delta B1 will be, this will be minus 10 upon 3EI into 3 by 4 cube. So minus 10 upon 3EI into 3 by 4 cube. Then delta B2 is minus 2.5 upon 2EI into 3 by 4 square. So minus 2.5 upon 2EI into 3 by 4 square. And you have VB into 3 by 4 cube upon 3EI. So plus VB upon 3EI into 3 by 4 cube equal to 0. Get me the value of VB from here. Please calculate VB from here. Avinash sir, Prajat sir, please tell me the value of VB from here. It's a big calculation. I need the answer. Please calculate VB. So I think VB will come out as 15 kilonewton. Check this out. VB will come out as 15 kilonewton. VB will come out as 15 kilonewton. Now once you got the value of VB, you can take summation of vertical forces equal to 0. So you will write down summation of vertical forces equal to 0. Right. Now for which beam? For this beam. For this beam, or for this beam also you can write down, not a problem. But I will prefer this beam, right? The beam in which I haven't transferred the load. So here I have VA acting upwards, VB acting upwards, and then this 10 kilonewton load acting downward. So I will write down plus VA plus VB minus 10 equal to 0. So you have VB is 15, so VA will be 10 minus 15, that is minus 5. Means whatever direction of VA we have assumed, we have to reverse that direction. VA will be acting 5 kilonewton downwards. Now once you got the value of VA, next is calculate the moment reaction at A. So for that you can write down summation of moment about A equal to 0. So summation of moment about A equal to 0. So the first moment will be minus MA. Okay, first moment will be here minus MA. Minus MA. Next will be, you have the anti-clockwise moment due to VB. Value will be VB into 3 by 4. So minus VB into 3 by 4. The next moment will be due to this 10 kilonewton load. Value will be 10 into 1 and it's a clockwise moment. So plus 10 into 1. So you have MA is equal to VB is 15. So when you take it that side, it will be, sorry, you keep it here only. So this is minus 15 into 3 by 4 plus 10. So this will be how much? Please calculate MA. So I think MA also you are getting negative, means whatever direction you have assumed, you have to reverse that direction. So please find out the value of MA. So this will be minus 15 into 0.75 plus 10. So this is minus 1.25. So MA is minus 1.25 kilonewton meter. Okay. So this is your beam. So you have VA, VB acting like this, VA acting like this, and MA is acting like this. This is how MA is acting. MA is 1.25 kilonewton meter. This is 5 kilonewton. This is 15 kilonewton. And then this is 10 kilonewton, right? Longer method will be drawing the entire bending moment diagram. Shorter method will be, since I know that over this portion, say this is A, B and C, over this portion BC, this entire length will be hogging, right? So bending moment over this portion BC will be negative and it will never going to cross the line, means cross the sign, right? It will never going to change the sign. So what I will do, I will directly consider my section XX on this portion AB and I will measure the distance of this section XX from this free end C, right? So what is the value of bending moment over this section X? This is equal to, you have the hogging moment due to 10 kilonewton load, value will be 10 into X, and you will have the sagging moment due to VB, so plus, so I will first write down minus 10 into X and plus VB, so VB is 15 into X minus 0.25. This distance is 0.25 na, this is 0.25 meter, so this distance will be X minus 0.25. Now simply equate this bending moment equal to 0 and you will get the location where bending moment will change its sign. Just equate this to 0. So for point of contraflexure, bending moment should change its sign. Should change its sign. Bending moment should change its sign, and wherever bending moment will change its sign, the value of bending moment at that section is 0. So what I will do is, I will simply equate bending moment at section X equal to 0. So that is equal to minus 10X plus 15 into X minus 0.25. This will going to give you the location where you will have the point of contraflexure. So this is 10x minus 10x plus 15x will be 5x, and this will be minus 15 into 0.25 equal to 0. So you will have x is equal to, this will be 3, 0.75 meter from your free end. So from your free end, the point of contraflexure will be at a distance of 0.75, right? So from the free end, if it is 0.75, then from end A, it will be 0.25. So point of contraflexure will be, at a distance of, 0.25 meter from A. From C it is 0.75, so from A it will be 0.25. So like this you need to solve this question, okay. Let's move ahead with this. The next is the strain energies, right. My dear, a lot of students have a lot of confusion regarding strain energy. Strain energy is basically due to the deformations caused in the structures, and deformation is caused by the external load. Now due to external load, there can be 4 different types of forces that can be present in any structure. First one is the axial force, second one is the shear force, third is the bending moment, and fourth is the twisting moment. These 4 different forces will cause 4 different deformations, and every deformation will have its strain energy. Word itself says strain energy. Energy is stored in the body due to deformation by external load is termed as strain energy, right. Axial deformation will have axial strain energy, shear deformation will have shear strain energy, then bending deformation will have bending strain energy. I have prepared one chart for you, and torsional deformation will have torsional strain energy. Let me just give you an idea. I think I have a chart here, yeah. Yes, this is the chart. You can see this. So strain energy due to bending is integration of mx square dx upon 2ei. Then you have strain energy due to shear is Vx square dx upon 2Ag. Then strain energy due to torsion is U integration of Tx square dx upon 2Gj. One more thing I would like to tell here, I think it is previously written, that strain energy due to axial deformation is Px square dx upon 2Ae. This is strain energy due to axial deformation. P square L upon 2A, that is strain energy due to axial deformation, right. Axial strain energy due to gradual loading condition is half P into delta. So strain energy is always calculated using load deformation curve, and strain energy due to impact loading is P into delta, okay sir. Out of all these deformations, for example, if a beam is subjected to axial, shear, bending and twisting deformation, then bending deformations are more significant. So for rigid frames, if they are asking you to find out the strain energy, you will only calculate due to bending deformations. But if they are asking you to calculate strain energy of a truss, I am precisely taking the word so that you don't have any confusion. If they are asking you to calculate strain energy stored in a truss members only contain axial forces. So you have to simply find out the strain energy only due to axial deformation for a truss. For beams and any other rigid frames, you have to calculate strain energy only due to bending, right. So let's see one question. So here you need to find out the strain energy stored in the truss. So first of all, I would like to tell you the strain energy of a truss is the sum of the strain energy of the members. So total strain energy is sum of strain energy stored in the member AC plus strain energy stored in the member BC. The total strain energy is the sum of strain energy in the member AC plus sum of strain energy in the member BC. For that, I need to find out the member forces. So let me assume the direction. This is member force FAC and this is member force FBC, right? One thing is, you consider the equilibrium of this joint C. Write down summation of vertical force is equal to 0, summation of horizontal force is equal to 0. You can solve it. Or you can directly apply Lemmy's theorem here, right? So by Lemmy's theorem, what I can write is, by Lemmy's theorem, what I can do here is, check this out. This is my force in the member AC. This is force in the member BC. And this is the external load, right? This angle, okay. This angle is 45. So what will be this total angle? This total angle will be 135. Okay. Similarly, this angle will be also 135. This angle will be 90 degree. You can do the geometry, no problem with that. This is 90, this is 135, this is 135. This is force in the member AC, and this is force in the member BC, and this is the external load W, right? So what I can write is W upon sine 90. You have to take the opposite angle. W upon sine 90, W upon sine 90 is equal to FAC upon sine 135. FAC upon sine 135 is equal to FBC upon sine 135. FBC upon sine 135. FBC upon sine 135, right? This will help you to directly calculate the value of FAC and FBC. Now you can simply take this first two ratios. So FAC will be W into sine 135 by sine 90. So I will write down FAC is W into sine 135 by sine 90. So sine 135 is nothing but cos 45, and cos 45 is 1 by root 2. So here you have FAC is equal to W by root 2. FAC will be W by root 2. In the same note, you can calculate FBC. So you will write down FBC is equal to W into sine 135 upon sine 90. So from here also FBC is equal to W by root 2. So you have calculated both the member forces. Now you have to find out the strain energy. Check this out. So strain energy stored in the member AC, strain energy stored in the member AC is equal to force in the member AC. So I will write down FAC square into length of member AC divided by 2 times of AE. Okay. Axial rigidity of these members is AE here, but here axial rigidity is 2AE. That you need to take care, right? Length of this member is L. So calculate this. Strain energy stored in the member AC is equal to FAC is W by root 2. So I will write down W by root 2 square into L upon 2AE. So this is equal to W square L upon 4AE. W square L upon 4AE. This is the amount of strain energy stored in the member AC. Now calculate strain energy stored in the member BC. Strain energy stored in the member BC is force in the member BC square into length of member BC divided by 2 times of axial rigidity of member AC, which is 2AE. Right, this is axial rigidity for member BC, which is 2AE. Substitute force in the member BC. So this will be W by root 2 square into L upon 2 to the 4AE. So this will be how much? Strain energy stored in the member BC is equal to W square L upon 8AE. This will be W square L upon 8AE. So you have strain energy for member BC, strain energy for AC. Add both of them to calculate total strain energy. So total strain energy is W square L upon 4 AE plus W square L upon 8 AE. And when you do the calculation, you will find out that strain energy is 3 W square L upon 8 AE. This is 3 W square upon 8 AE. This is how you need to do it. Please do it. Do it quickly. Okay, now let's see this. Next is the Castigliano's theorem. If you want to find out the deflection under the load in the direction of load, then partially differentiate the total strain energy with respect to the load. So the deflection in the direction of load at the point of application of the load is the partial derivative of total strain energy with respect to the load. If moment is acting and you partially differentiate strain energy with respect to the moment, you will get rotation at that point. Okay. And this is termed as Castigliano's first theorem. Let's see this. So again, I will take the same bracket and they are asking you to find out the vertical deflection at this point C. So what is vertical deflection at point C? So vertical deflection at point C, delta vertical at C, vertical deflection at point C is the partial derivative of total strain energy with respect to the load. Means whatever previously you have calculated as the strain energy, you have to partially differentiate it with respect to W, and that will going to give you the vertical deflection of this point C. So what is the strain energy you have calculated? 3 W square L upon 8 AE. Please partially differentiate this. So delta vertical at C is equal to, this will be 3 into 2 WL upon 8 AE. So delta vertical of C is 3 by 4 WL upon AE. The only limitation with this method is you cannot calculate the horizontal deflection. Means you can only find out the deflection at the point of application of load, and that too in the direction of application of load. So theta is equals to D strain energy by dm. Yes, Avinash sir. Theta is equals to D strain energy by dm. Yeah. Sorry. Very sorry. This is theta B, and theta B is equals to del U upon del M. Theta B is equals to del U upon del M. Please have this. Thank you so much, Avinash sir. Okay. Chalo. So this announcement I have already done. You have seen that how these question practice is actually helping you to revise these questions frequently, like concepts frequently, and do your subject more quickly. You will have more benefit if you start attempting this test series. I am telling you, in these last 2 months, the primary target should be cover as much as test possible. Means the day of gate examination should not feel new to you. It should be a condition that in which you have already been in. You have acclimatized yourself in such a competitive environment, and for that reason, start attempting the test series very rigorously. Very means literally very rigorously. Start attempting the chapter test, analyze your weak areas, then attempt the subject test, analyze your weak areas. Make a list of your weak areas and then plan your revision accordingly. Don't go blindly revising any subject without knowing your weak areas and without knowing your strength. These 2 months are the months of working in your weak areas, improving your weak areas, and in the same way improving your strength. Means if you just practice questions from your strong area, it will not do any benefit, right? You will get the benefit when you start practicing your weak areas, and that can be only identified by attempting the test series. So this is my personal request to you. Anywhere if you are preparing, have this test series. It is offered to you at a discounted price of 20%. We are offering you with 130 plus online test. Is starting from the chapter test, subject test, multiple subject test, advanced subject test, and the full length mock test. And the best thing is you are getting a 33 years GATE question booklet of maths, aptitude and technical subject. You are getting a doubt solving portal. Just visualize this in these last 2 months. If your doubts are not cleared properly, how badly it can affect your preparation. You are getting a post-GATE guidance program in which if you get any rank and if you want to have a counseling session regarding your choice filling, or if you want to have mock interviews, all these things will be provided to you in this course of Test Series Plus that we have launched exclusively for you at a discounted price of 20%. Most of the students ask us, sir, where do we get your material? So sir, this is the thing. The Google form is provided to you in the description box. You can just click in the Google form, fill in the details and enjoy the test series. We at IMS GATE Academy, I would like to repeat again, we offer you 4 different types of courses where we are providing you with 800 hours of live teaching with doubt solving and interaction. We provide you with theory and exercise book containing 4,000 practice questions, well versed in level 1, level 2 and level 3, so that even you have a proper idea at which level your preparation is. We provide you with the 33-year GATE question bank. It's one of the premium product that we are providing at IMS GATE Academy, along with the flagship program of mentoring. We provide you with the 12 personalized one-to-one mentoring sessions so that you stay focused, oriented, motivated and well charged throughout your preparation journey. My dear, if you are clear in your mind what you need to do, definitely you can achieve it in very less time, and that is how these mentoring sessions, my plan sessions, is helping our student to the next level. At IMS GATE Academy, we have a culture of learn, practice and test. Learning, practice and test is done systematically by the top-notch mentors of IMS GATE Academy. Because we have a well-designed course, we stick with the subjects in such a way so that most of the questions that are coming in the GATE examination can come directly from the notes. And if the question is not coming directly from the notes, you know the concept in such a way that you can handle that question easily. So this is what I want to offer for today for structural analysis. Whatever was possible from my end, I have tried to do it quickly. I hope this session will be helpful for you. And if this session is helpful, don't forget to share with your friends. And if you haven't subscribed to our channel, please hit the like button and subscribe to our channel. Thank you so much, my dear students, for listening patiently. I wish you all the best. And just a small update, tomorrow construction material and management session will be from 3 p.m. onwards. So I'll see you tomorrow at the same YouTube platform of IMS GATE Academy. This is Prateek Mishra, your lead mentor for civil engineering at IMS GATE Academy, signing off with a smile. Please take care.